Okay, this is Lecture 9, Part 3, although it doesn't really matter which order you watch the Lecture 9 videos on because they're subject specific, and the subject is polarity. I'm going to start by showing part of a video, and I have put the link in Canvas, and I encourage you to watch the whole thing, but a lot of it is concepts we're actually going to learn in Chem 1, but it's a great little video, and I'm going to let it serve as the introduction to polarity. Oops, no, not that, this. So it's from TED Talks. Like I said, I'm going to play about half of it, but go to the link. It's called Polarity of Water Explained under Module 6, and it's a lot of fun. It's worth watching it, the whole thing.
How come some insects are able to walk on the surface of a pond, but you quickly sink to the bottom when you try to walk on water? And why do lakes freeze from the top down in winter? In a word, the answer to all of these questions is polarity. Water is a simple molecule made up of one oxygen atom and two hydrogen atoms, but it is essential to life. In fact, water makes up approximately 60% of the adult human being's body weight. The polarity within those water molecules gives this common substance the properties that make it unique and life-sustaining. Polarity refers to the unequal sharing of electrons within a molecule. For water, the bonding between the oxygen atom and two hydrogen atoms within a single water molecule is like a tug of war between a big, strong football player and a cute little toddler. Oxygen is a larger atom with more protons in its nucleus than hydrogen. These positive charges are like a person's physical strength. They are able to attract the negatively charged electrons in the bond, just like a strong individual is able to overpower a weaker individual in a tug of war. So, oxygen is able to attract more than its fair share of electrons. Because hydrogen is smaller and has less strength, or fewer protons, it loses the tug of war and attracts fewer than its fair share of electrons. So the oxygen in water behaves as though it's negative, and the hydrogens behave as though they're positive.
Okay, so the rest of it is very interesting, and I encourage you to watch it, but that's just the polarity part. So that is what polarity is. It is the uneven distribution within a molecule of electrons. If you go back to the electronegativity, this is the reason for polarity. So remember, electronegativity is the measure of an atom's ability to attract electrons and to have more electrons. So here's oxygen over here, more electronegative than hydrogen. Hydrogen is 2.2, oxygen is 3.4. These are electronegative values, and they're measured in the lab. Remember, it increases as you go across, and it increases as you go up. Fluorine is the most electronegative. So everything's headed towards fluorine, right? So if you have atoms with different electronegativities bonded, you have an unequal distribution of the electrons in that bond because of this trait. And they are still shared. I don't want you to think from that video that hydrogen didn't get any of the electrons. She got some. It's just that most of them hang out around oxygen. Okay, so it's still a shared bond. It's still covalent, but it's not an equal distribution of electrons. So polarity is about specifically poles, just like we have a North Pole and a South Pole. That's what it refers to. You have one end, one pole of the molecule that's got more of a negative charge, and one end, one pole that's got more of a positive charge. So you have specific, you have different poles. Like I said, we have a North Pole and a South Pole in the planet Earth. Well, molecules have poles too, if they're polar. If you have perfect sharing, if you have two identical molecules, you have an oxygen bonded with an oxygen, a fluorine bonded with a fluorine, you have perfect sharing because, of course, they have the same electronegativity. You have no difference. So it's the difference in electronegativity that leads to polarity. Okay? And the greater the difference, the larger the polarity. So this is going to cover how you determine what's polar and nonpolar. Now, the one thing is in this course, we are not going to have a cutoff point. Later, you will actually measure. You'll measure the difference. You'll add up the difference between the electronegativities, and there's a cutoff point, and you say if it's 0.5 and below, it's nonpolar. If it's 0.5 and above, it's polar. We're going to keep it simple. It's either polar or nonpolar, which means if there's any disparity, any difference, you have polarity. It also, though, has to do with the shape, as we're going to see, because that tug of war, if you're tugging from the opposite directions equally, it cancels out. So you have no net just change in distribution. It's even on both sides. So I'm going to get to that. So polarity has to do with the shape and electronegativity. The other thing we're doing in this class to keep it simple is if you have an ion, we're just calling it ionic. So you have three choices for a molecule. If you're asked if it's polar, you can either answer it's polar, it's nonpolar, or it's ionic. Any ionic molecule we're just saying ionic because there's no sharing. And this has to do with the sharing of electrons. As the video talked about, it talked about the strength of oxygen, and also the size matters because fluorine, it not only has a very high centered positive charge, it's a very small radius. It's a very tiny atom. And so electrons are able to get closer to that positive charge. So it's the most electronegative because of a combination of its small size, its small radius, and its high positive charge. Whereas chlorine, yes, it's got an even higher positive charge, but it's also got a larger radius. So by the time that positive proton charge gets felt out here, first of all, it's being felt by all of these electrons in between. So we call it shielding, right? It's kind of like cotton in the way. Let's say this is noise and this is a bunch of cotton. You're not going to hear the noise as well out here as you would out here because of all the interference. Okay, so it's radius and that positive charge that contribute to electronegativity. And it's the same force equation. It's directly related to charge. The higher the charges, the stronger the pull, but inversely related to radius. So the bigger the radius, the smaller the number, the force. All right, electronegativity. All right. So make sure you understand the trends in electronegativity across a row. If you want to know which is the most electronegative, here you want to know which one is furthest right. Well, fluorine is the most electronegative of the entire periodic table, so of course the answer here is fluorine. What about down as a group? It gets weaker as you go down because your radius is getting bigger. So if we go back to the periodic table, and this is oxygen, sulfur, selenium, and I don't remember, tellurium or something, I think that's called. I can spell it better than I can say it. Your electronegativity increases as you go up, so it has to be the oxygen. And if you mix rows in groups, iodine, bromine, chlorine, sulfur, phosphorus, iodine, bromine, chlorine, so the chlorine is going to be more than iodine, bromine because it's higher. Sulfur and phosphorus were the other two choices. Well, chlorine is to the right of sulfur and phosphorus, and it's above iodine and bromine, so it has to be in that list the most electronegative. So look at this, pull up your own periodic table, and follow this trend, and you should be able to see that chlorine is the most electronegative. All right, This is, so we are not doing the math thing. You'll do that in a later, probably Chem 2. So we are simply saying polar, nonpolar, or ionic. Here's an example of polarity. This is what it actually looks like. This is an electrostatic potential map. But what is the potential? Now, the potential, of course, is an electrical charge. It comes from electrons. We talk about electrons as a cloud. So this cloud has a higher probability around the fluorine. You're going to have a higher probability of finding more electrons and less around the hydrogen because of the electronegativity. And this is, in fact, the energy measurement you get for hydrogen fluoride. And it's computer colorized for red to be greater density or hotter, blue to be cooler. But there's still electron sharing going across the whole thing. The electrons are circulating around both nuclei. It's just that they're spending more time circulating around fluorine than around hydrogen. Therefore, you get the fluorine end has a more negative charge. That's your pole. And the hydrogen has a more positive charge because the electron flow is in this direction. We show that with a vector. A vector is an arrow with a handle on it. Don't forget your handle there. It's like a sword. It goes in the direction of the electrons. This little symbol, we call this a dipole moment. It's how we describe the pole. We don't say negative pole, positive pole. We say it has a negative dipole moment and a positive dipole moment. So that's just terminology. And we draw the little, I think it's a delta S, delta positive, delta negative. I think that's a delta. Yeah. Okay. So the core issue of polarity is difference in electronegativity, but shape also has a role. Skip that. So if you had to ask NO, that's going to be linear. It's just two atoms. Oxygen is more electronegative than nitrogen. Therefore, your polarity would be, there would be polarity because there is a difference in electronegativity, and it's toward the more electronegative. It's towards the oxygen. So it's B. Which bonds are polar? Where do you have a difference in? Notice that these are all covalent bonds, all right? Because this has to be for covalent bonds. Shared electrons. You have to have a difference in electronegativity. The only time in this class we do not have a difference in electronegativity is if we have the same atoms. We're not doing the measurement thing, which means that 1, 3, 4, and 5, or all but 2, E is the answer. Okay, so polarity involves the shape of the molecule and electronegativity differences. So how does the shape have an effect? Okay, sorry. I'd make sure I was recording. How does the shape have an effect? If you have an equal opposite pull, so that's that tug of war, but you got the big football guy here and the big football guy here, you have an equal and opposite pull on the center atom. Therefore, the electrons are distributed over the entire molecule equally. In other words, there's symmetry. This end and this end are the same because of the equal opposite pull. It cancels out because a vector is direction and force. So therefore, this is nonpolar because the same atoms on either side, and it's linear. That's the shape aspect. Carbon tetrachloride, this is tetrahedral. You have perfect placement of each atom away from the center with the exact same angle, bond angle between them all. So even though chlorine is very electronegative, you have an equal and opposite pull from each one. It cancels out. This is nonpolar because, and here's the actual image of carbon tetrachloride. You see the outside poles are all the same. So when you stand outside of a molecule, you want to say, is it evenly distributed? Do we have symmetry? Yes. There's no hot spots. Both poles are the same here. All my poles are the same here. Okay. Whereas if you have a shape, a V, so your AXE, you've got some E there. If you have some E, you're going to have polarity. So the example given in the video is water. Water, of course, has two bonds, but also two unshared pairs. So the unshared pairs are going to bend the OH bonds closer together. So you have a V-shaped or a bent configuration. You have these unshared electron pairs up here, right? So we have two things going on. You have all this electron density up here from the unshared electron pairs from your dots. They're circulating up here. But you also have the fact that oxygen is more electronegative than hydrogen, so it's pulling hydrogen's electrons slightly towards itself. So therefore, you get a higher electron density over the oxygen, and we give that the negative dipole moment, and less electron density around the hydrogens. And again, this is a real image of water. We put the molecule polarity. This is bond polarity. Each bond you can draw the polarity of. The hydrogen electrons are going towards oxygen. The molecule polarity is you take the sum of the overall. Vectors are additive. And basically you give a vectors pointing in the direction of electrons for the overall molecule. Here it's going up towards the oxygen. That's where the electrons are going. Okay, so for your vector, if we ask you for the molecule's polarity, give it for the entire molecule, not just the individual bonds. Here, this is also bent because you have an unshared pair here. This is AX2E. So it's a trigonal planar spinner electron group arrangement, but because of this unshared pair here, it's up here, it's pushing these in. So you have a bent or V-shaped arrangement, molecular shape. Oxygen is more electronegative than sulfur. If you look on your periodic table, sulfur is below oxygen. And remember, as we go up, electronegativity increases. Therefore, the electrons are going to go in the direction of the more electronegative atom. This time it's oxygen, and this time the oxygens are at the ends. So they're pulling some of the electron concentration or cloud, or however you want to think of it, towards themselves. That's just what happens. And when you have your image, sure enough, you have the hot spots around the oxygens. And we show that the polarity for the molecule, the whole molecule is downward, is towards the oxygens. And we do it towards the middle. We go down the middle of these two oxygens. Okay, it's additive, so we go straight down the middle. So that's how we draw the polarity for a molecule. It has to do with the difference in electronegativity, and it has to do with the shape. So you have to do VSEPR in order to determine if there is in fact polarity. So here's some more examples of polar, nonpolar, linear. Now the green are the same atom, the red is another one. So you have a situation here where you have the same atom on either side, so it would balance out. However, if this were if this were an oxygen, this were a carbon, and this were a sulfur, you would have a polarity toward the oxygen. So if they are different atoms, you would have a polarity towards the more electronegative one, and that would be over here. However, in this picture, they're the same atom, and so you have an equal and opposite pole. Same thing. So all of your electron group arrangements, if there are no substitutions, if you have the same atom on each it's going to be nonpolar because you have equal and opposite pole. But as soon as you have an E in there, you have an electron group. You have AX2E, AX3E, AX2E2. You have polarity because first of all, you've got an electron density right here that's not being shared, but also you now have angles introduced. So it's just know that if you have one of these configurations, you are going to have polarity. What you have to determine is which direction it's going, upward toward the center molecule or downward toward 2 or 3 or 1 of the external, the connected atoms. Okay. So I'm going to do this on the whiteboard, but I want to show you how we draw this, the vector. Pretend there's a handle on this for a vector. If you have 1, and this is for a tetrahedral, 2 or 3 polar atoms pulling away from the center. So I'm going to go to the whiteboard. So I have carbon, and I have a carbon that has 3 hydrogens and 1 chlorine. I have 2 of each, and I have 1 hydrogen and 3 chlorines. All right, so start with, I'm going to draw the structure, the molecular shape, the Vesper, as best I can. I'll put my chlorine here, my hydrogen, hydrogen, hydrogen. Okay. Hang on, that bugs me. Sorry. Anyways, this is obviously more electronegative. So it's introducing polarity. Now you could do a bond polarity, and it might help you figure out where the polarity is. That's fine. So if we do a bond polarity, we say the hydrogen is less electronegative than the carbon. And so each bond, the electrons are moving in this direction towards the carbon. But the chlorine is more electronegative than the carbon. Okay, so those are my bond polarity. My molecule polarity we do is a bigger one over the whole thing. And of course it goes in the direction of the carbon. And I only have 1 carbon, so that makes it really easy. You draw the polar arrow in the direction of that atom. So that's super easy. All right, what if we have 2 chlorines? So I'm going to take this hydrogen and make it a chlorine. Again, it's easy because if I do my bond polarity, and you don't have to, but the electrons are being pulled away from the carbon in that direction towards each of the chlorines. With vectors, they're additive. So if you have one going this way and one have this way, your molecule polarity is between them, okay? So it's like a V. And I don't know if my picture is in the way. So you draw them like in a V, and then you just draw the arrow out in between them. So that's if you have 2. This is on a tetrahedral. You'll get this a lot. 2 electronegative atoms. And we're talking about the same ones. We're not going to make it super difficult for you by giving you, a chlorine and a fluorine. No. All right. So I'm going to do 3, but this time I'm going to put the chlorines down on the bottom because it makes it easier to show how to do the arrow. This is, what, I'm just going to redraw this. So this time my chlorines, and I do them on the bottom because it just makes it easier to draw the vector. Of course, the individual bond polarity, the hydrogen is going towards the carbon because carbon's more electronegative, but the chlorines are drawing the electrons away from the carbon. So we show this 1, 2, 3, these are equally spaced, and we show the arrow, when you have 3, the vector goes straight down. So think of that as straight down the middle of that carbon. And those chlorines are around it like an umbrella, like it's the handle of an umbrella, okay? And those chlorines are part of the umbrella over it. They're pulling out, and so the vector is additive, it's straight down. So just remember, 1 goes in the direction of the atom. 2 goes in between. If you have 2 atoms, you put the vector between the 2. If you have 3, draw your atoms like in this conformation, and it's straight down below. Now, if I had the chlorine over here, raise my vote, you could put it kind of this way, right? And that's pretty clear that it's between this one, this one, this one. So put it between the 3. So that's how you draw the vector in a tetrahedral when you have multiple electronegative atoms. And like I said, I don't think we're going to give you some kind of a mixture that makes it difficult. We want you to know that you have the core concept down and can apply the core concept. Okay, so let me go back to let me go to this slide. I don't know why it does this. So that's this slide. This is just repeating what I just explained. And, you know, in this case, the nitrogen is more covalent. So the pull is towards the nitrogen. And we have an E there, so it's going to be up toward the nitrogen. So what's the polarity? Let's work through some of these. What's the polarity for this molecule? You simply look up what's the most electronegative. Because you have a trigonal planar, you have an AX3. Oxygen is more electronegative than sulfur. Now let's go back to this slide right here. When I have an AX3 and my surrounding atoms are the same, they're giving an equal and opposite pull, and it is nonpolar, okay? So because of that, I'm getting caught up with the double bond because there's a part of my brain that wants to delve into that deeper, but we'll just keep it simple. And this is nonpolar because it has 3 oxygens in equal spacing around the sulfur. All right, now what about this one though? We have a trigonal planar again. We have an AX3. AX3 is trigonal planar, but we do not have the same atoms around the central anymore. So the carbon, of course, is more electronegative than hydrogen, but oxygen is more electronegative than carbon. So it's going to be in the direction of the oxygen, and your polar vector, your polarity vector is B. Okay, do you see that? In the direction of the more electronegative atom. What about this one? All right, let's look on the periodic table. If you look on the periodic table, you'll find that, or I'll go to the electronegativity table. Phosphorus and fluorine. Come on. Here we go. So here's phosphorus and here's fluorine. I told you fluorine is the most electronegative atom. So anytime you see that, you know that, but it's 4.0, phosphorus is 2.2. So obviously fluorine is the more electronegative. So the electrons are going to flow in that direction. This is your umbrella. So your polarity is going to go down, the handle of the umbrella is going to go down towards the fluorines, but straight down. So it's E, okay, because you have 3 of them. This is the problem I just worked out on the board. What about this one? Again, I have fluorines, the most electronegative, but I only have 2. So you go in between the 2 is your vector. So that's D, all right? So which of these would be polar? Well, I can tell you oxygen is nonpolar because it's a molecule with itself. There's no change in electronegativity. CCl4, carbon tetrachloride, this is tetrahedral. That carbon is surrounded by 4 chlorines. They are equal and opposite. So that is not polar. But if we drew this out, this is linear. So the electrons would flow towards the nitrogen here. CH2Cl2, it would be in between the 2 chlorines. So you have 1 carbon surrounded by 2 hydrogens and 2 chlorines. Again, it's tetrahedral. This is the example I did on the whiteboard. And so it would be, I lost my mouse, in between the 2 chlorines. And SCl2, I would have to draw out. What does SCl2 look like? Um, 7, 14 plus sulfur is 6, 20, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so SCl is bent, right? Yes. Yes, because we're not going to give chlorine double bonds. Yeah, so this is an AX2E2. So if you draw an AX2E2, you will see that this is bent. Because chlorine is not going to have double bonds. So since it's bent, yes, this has polarity. So 5, 3, and 2 are polar. So A. And I did a separate video on multi-centered molecules. If you have a polyatomic, even though this is covalent, we call this ionic. So if you get this on a test, or Alex, the answer is ionic. It's not polar or nonpolar because it's an ion. So any ion, you just tell us ionic. That's your easiest one. The trick is remembering it, which I know isn't always as easy as we make it sound. And I think that is it. All right, so good luck and come with questions. And that is the end of lecture 9, all parts.